I want you to just look down at your hand for a second. If you really look at it, it seems incredibly solid, doesn't it?
Yeah, totally solid.
Right, and the desk or table in front of you, also completely solid. But if we take the most successful, rigorously tested scientific theory in the entire history of human civilization and apply it to your hand right now, well, that theory tells us something terrifying.
Oh, it really does.
It tells us that there is a non-zero, mathematically proven probability that your solid hand could just pass straight through that solid table.
I mean, it sounds like bad science fiction, right? Or like a glitch in a video game.
Yeah.
But it's actually a fundamental truth of the universe we live in. When you zoom in close enough, the whole comforting illusion of a solid, predictable reality just completely falls apart.
And that is the perfect way to frame what we're doing today. So, welcome to a very special deep dive. Today, we're exploring the absolute bedrock of reality, which is quantum mechanics.
It's a huge topic.
It is. And right at the outset, we really have to talk about this massive reputation problem the topic has, because quantum mechanics exists in this deeply hilarious contradiction.
Oh, yeah. The dichotomy is wild.
Right. On one hand, it's the single most verified scientific theory ever conceived. Like, we have confirmed its predictions to more decimal places than almost anything else human beings have ever attempted to measure.
And yet, flip a coin, and it is simultaneously the most frequently invoked phrase used to justify complete, absolute nonsense.
It's the buzzword of choice. I mean, it's the literal bedrock of our modern technological world, like the reason the device you're listening to this on even functions, but it's also the favorite phrase for, someone at a retreat trying to sell you a special tuning fork that supposedly, what is it?
Quantum aligns your cellular vibration.
Yes, that exactly. Which brings us to the core mission for this deep dive.
Yeah.
If you're listening to this right now, we're operating under the assumption that you have zero prior background in physics.
None required. You don't need to know any math for this at all.
Right. Our singular goal today is to build an accurate foundational picture in your mind of what quantum mechanics actually says. We are going to draw a thick, incredibly sharp line in the sand between the genuine, mind-bending strangeness of actual physics and, well, the New Age mysticism that tries to hijack that strangeness to sell you things.
It's a really important line to draw.
It is, and we're going to take our time. Consider this an unhurried journey. We're going to use everyday analogies. We are going to stumble through the confusing parts together. And honestly, I'm going to ask all the seemingly dumb questions.
Please do. That's the best way to do this.
Because the goal here isn't just to memorize some trivia to sound smart at a dinner party. The goal is deep, fundamental understanding. I want you to really feel the texture of how weird the universe is. So where do we even begin?
Well, to understand why anyone ever bothered to come up with quantum mechanics, we actually have to start by looking at a catastrophic failure.
A failure. Okay, I love a good disaster. Set the scene for us.
So we need to step back to the very end of the 19th century, let's say around the year 1899. At this point in history, physics was built on a framework that we now refer to as classical physics. And it was, frankly, a masterpiece.
It really was.
It rested heavily on two monumental pillars. First, you had Isaac Newton's laws of mechanics. This is the math that perfectly explained gravity, motion, and, how massive physical objects bumped into each other.
Apples falling from trees, planets orbiting, that kind of stuff.
Exactly. And second, you had James Clerk Maxwell's theory of electromagnetism, which finally explained light, electricity, and magnetism as part of a single unified phenomenon.
And it is hard to overstate how successful this was, right? I mean, these weren't just abstract ideas. They were the theories that literally built the Industrial Revolution.
Oh, absolutely.
They explained the exact orbit of the planets. They could calculate the precise arc of a cannonball, the thermodynamics of massive steam engines, the way radio waves transmitted invisible signals across oceans. Classical physics basically handled the entire macroscopic world flawlessly.
It did. And because of that, the scientific community at the time was experiencing a profound sense of smugness.
I can imagine.
Yeah. Lord Kelvin, a really brilliant and famous physicist of the era, he gave a speech where he essentially suggested that physics was mostly, finished.
Finished. Like, we solved it, guys. Wrap it up.
Pretty much. The grand mysteries were solved. The general sentiment was that all that was left for future generations of scientists to do was just measure the known constants of the universe to a few more decimal places.
Talk about famous last words.
Right.
Because they decided, hey, since these rules work so perfectly for planets and steam engines, let's just apply those exact same rules to the microscopic world.
Which is a totally logical leap.
Sure. So they started looking closely at atoms and at the specific nature of light interacting with matter. And this is where the vehicle just completely drives off the cliff.
It's a spectacular crash.
Yeah, classical physics didn't just make a tiny error that needed a small mathematical tweak. It produced answers that were physically impossible.
Right. The breakdown was just massive. The historical record highlights two glaring failures that essentially forced the invention of quantum mechanics. So let's look at the first one. It's the problem of hot objects radiating heat and light. Historically, it's known as the ultraviolet catastrophe.
Okay, that sounds like an awesome band name, but break that down for me. What does classical physics say should happen when I, heat up a piece of metal in a fire?
So according to the flawless rules of Maxwell's electromagnetism, a heated object should radiate energy. That part is true.
Right, it glows, it gets warm.
But the math insisted that as the wavelength of the light gets shorter, so moving from red light to blue light to invisible ultraviolet light, the object should emit more and more energy exponentially.
Okay.
In fact, classical physics predicted that a completely normal hot object should radiate infinite energy at those short wavelengths.
Wait, infinite? Meaning, if I strike a match, the math says that tiny little flame should instantly emit a blinding, world-destroying blast of infinite ultraviolet radiation.
Precisely. Yeah. Which, obviously does not happen, or the universe would have incinerated itself the moment the first star ignited.
I feel like we'd notice that.
We definitely would. The
Like,
classical equations literally blew up to infinity. They were utterly broken.
Wow. And the second failure is even more wild because it basically makes my own existence an impossibility. Classical physics predicted that atoms shouldn't be able to hold themselves together for more than a fraction of a second.
Yeah, it's a huge problem. Think about the classic image of an atom you probably saw in middle school. You have a dense nucleus in the center and little electrons orbiting around it, sort of like planets orbiting the sun.
Like the Jimmy Neutron logo.
Exactly that image. But classical electromagnetic theory states that any charged particle, like an electron, that is moving in a curved path must constantly radiate away its energy in the form of light.
Okay.
And if it's constantly losing energy, it must slow down. If it slows down, the orbit decays.
Oh, I see. So the electron should just spiral inward, spinning faster and faster, losing energy until it just crashes directly into the nucleus.
Yep. And classical math calculated that this death spiral should take roughly 100 billionth of a second.
Good grief.
So the entire structure of matter should instantly collapse in on itself. Every atom in your body, the chair you're sitting on, the Earth itself, should just vanish in a microscopic flash.
So the leading scientific theory of the day proves conclusively that you, the listener sitting in your car right now, cannot physically exist.
And a major crisis.
The clockwork universe is officially broken, so who steps in to fix it?
The fix required someone willing to abandon a concept that felt so deeply intuitive, so obviously true to everyday human experience, that challenging it just seemed like madness.
Who was it?
The man who challenged it was a German physicist named Max Planck. He was obsessively working on that first problem, the match emitting infinite energy. He was playing with the math, trying to find literally any equation that would match the actual real-world measurements of a hot object.
And he finds a hack, right? Like a mathematical trick.
Yeah, he found an equation that worked perfectly. But to justify the equation, he had to introduce a completely radical assumption about the fundamental nature of reality.
Okay, what was it?
Well, for all of human history, we assumed that energy flowed in a smooth, continuous stream, like water flowing out of a faucet.
Okay, let's establish a really clear modern analogy for this. Because classical continuous energy versus quantum discrete energy is the absolute foundation of everything we're going to discuss today.
Definitely.
So let's think about money. Classical physics viewed energy like abstract money in a bank computer. You can divide it infinitely. You can calculate interest down to 1,000th of a cent, 1,000,000th of a cent. It's a perfectly continuous spectrum of value. You can move any infinitely small decimal point of money you want.
That is exactly how everyone, including Maxwell and Newton, thought the energy of light or heat worked. A perfectly smooth, infinitely divisible flow.
But Planck's math said that's not how the universe works. His math said the universe is actually a vending machine that only accepts exact physical change.
That's a fantastic analogy.
Right, because you cannot put half a physical penny into a machine. The penny is the absolute smallest indivisible block of currency. You can have 1 penny or 2 pennies, but you cannot physically hand someone 1.5 pennies.
Exactly.
So energy, Planck proposed, comes in these exact indivisible physical coins. He called these distinct packets quanta.
The energy is chunked. It has a fundamental granular resolution. Now, the crucial thing to understand here is that Max Planck himself didn't fully believe the physical reality of what he had proposed.
Wait, really?
Yeah, he thought he had just invented a clever mathematical trick to stop his equations from predicting infinity. He viewed it as a desperate measure.
That's wild. Okay, so enter Albert Einstein. Because Einstein looks at Planck's desperate mathematical hack and basically says, no, this isn't a trick. This is reality.
Precisely. In 1905, Einstein published a paper taking Planck's quanta to its extreme logical conclusion. Einstein proposed that light itself is not a continuous wave of energy, but is entirely composed of these little indivisible bullets of energy.
Yo.
Today, we call these indivisible packets of light photons.
Okay, let me stop you there, because my brain is already starting to itch.
Go for it.
If Einstein says light is made of tiny, solid bullets, photons, that implies light is a particle. But I know for a fact, and scientists in 1905 knew for a fact, that light is a wave.
Oh, yes, they did.
Like they had a century of indisputable experiments proving light acts exactly like ripples in a pond.
And this is where the profound discomfort begins. You're pointing out the exact friction that kept physicists up at night back then. The evidence for light being a wave was overwhelming. Waves diffract, they bend around corners. If a wave hits a rock in a stream, it wraps around it. Waves spread out across a massive area.
And particles absolutely do not do that. If I shoot a bullet at a rock, it doesn't gracefully wrap around the rock and continue on the other side.
No, it does not.
It hits the rock and stops. A particle travels in a straight line and hits a specific localized spot. It does not spread out.
So physics was suddenly staring into an abyss. They had an impossible contradiction. A century of classical experiments proved beyond any doubt that light behaves exactly like a continuous spreading ripple.
Right.
But Einstein's new math, which beautifully solved the infinite energy problem and perfectly explained new experiments, proved beyond any doubt that light behaves exactly like a stream of distinct localized bullets.
But how can it be both? A thing cannot be a tiny isolated pixel and a giant spreading ocean wave at the same time. That literally breaks the basic logic of human language.
It does break human language. And to truly visualize this impossible contradiction, to watch the universe basically break its own rules in real time, we have to look at one specific physical setup.
The big one.
Yeah, it is widely considered the most beautiful and most profound experiment in the history of science.
The double-slit experiment. It's almost cliche in physics at this point, but we have to spend serious time here. The entire mystery of the quantum realm, the deepest secrets of reality, are contained entirely within this one simple room. If you, the listener, can visualize this setup, you will grasp the core of the quantum revolution.
So let's construct this experiment in the mind's eye. Imagine you are standing in a completely dark, sealed room. A few feet in front of you is a barrier, a solid wall.
Okay, got it.
But cut into this wall are two very narrow vertical slits. They are parallel to each other, just a tiny fraction of a millimeter apart. Think of them as two very thin doors.
And behind that barrier at the far end of the room is a blank wall covered in photographic film, or like a highly sensitive digital screen, a screen designed to record permanently whatever hits it.
Exactly. So to set our baseline, let's leave the world of light for a moment and just imagine this barrier is sitting in a shallow pool of water.
Yeah.
We want to see what purely classical waves do.
Okay, water waves.
If you tap the surface of the water in front of the barrier, you create a circular ripple, a wave. That wave travels forward, hits the wall, and the water pushes through the two slits.
So what emerges on the other side of the wall are two new, smaller circular ripples, one from each slit. And as those two sets of ripples spread out across the pond toward the back wall, they have to overlap with each other.
Right. And this overlapping creates what is called an interference pattern.
I want to make sure we deeply understand interference because literally everything hinges on this. Imagine dropping two pebbles into a pond at the same time, near each other.
Perfect visual.
As the ripples spread and cross over one another, you see a specific pattern on the water's surface. Where the peak or crest of one ripple perfectly aligns with the crest of another ripple, they join forces. They amplify each other, creating an extra high wave.
But crucially, where the high crest of one wave perfectly aligns with the low trough of the other wave, they violently oppose each other. They cancel each other out entirely.
Right.
In that specific spot, the water becomes perfectly flat and calm.
Amplification and cancellation. So if we replace the water with a flashlight, and we shine a continuous beam of light at our two slits, what do we see on the photographic screen at the back of the room?
We see the exact same wave behavior. We do not just see two glowing lines of light directly behind the two slits.
Even though that's what common sense says should happen.
Exactly. Instead, the overlapping light waves hit the screen and create a sprawling pattern of alternating bright and dark vertical stripes. Bright stripe, dark stripe, dark stripe, dark stripe.
So the bright stripes are where the light waves met crest to crest and amplified.
Yeah.
And the dark gaps between them are where the waves met crest to trough and canceled each other into total darkness.
You got it.
So this is the ultimate smoking gun proof that light is a wave. It behaves identically to water.
Case closed. Until we introduce the quantum twist.
Here we go.
We know from Einstein that light isn't a continuous stream. It is made of indivisible chunks, the photons. So what happens if we dial down the power on our flashlight? We turn the intensity down so incredibly low that it is no longer emitting a beam. It is now acting like a microscopic pitching machine.
Firing one at a time.
Right. It fires one single solitary photon. Just one.
Click. One photon flies into the darkroom. We are now testing pure particle behavior. We are firing a single bullet. So when that single photon travels through the apparatus and hits the screen at the back, does it wash over the whole screen like a giant wave?
Absolutely not. A wave washes. A particle impacts. When that single photon hits the screen, it creates one tiny, perfectly sharp, microscopic flash of light. A single dot.
Okay, I am pushing back on behalf of the listener here because this is maddening. The photon hits as a distinct dot. A bullet hole. That is pure particle behavior. It did not spread out.
Correct.
So we fire another single photon. Click. A second dot appears on the screen in a totally different spot. We keep firing them, one single indivisible bullet at a time. Hours go by. Each photon travels completely alone. And when we look at the screen, these dots seem to be landing entirely randomly.
But they're not landing randomly. Because if you let this pitching machine run for days, and you allow millions of these individual isolated dots to accumulate on the screen.
This is the moment reality breaks, because as the millions of dots build up, they don't form a giant blob. They don't form two simple clumps behind the slits.
No, they go.
Magically, inexplicably, those millions of individual bullet holes arrange themselves to form the exact same striped interference pattern. Bright stripe of millions of dots, dark empty gap, bright stripe, dark gap.
We cannot rush past this. We really need to sit with how deeply impossible this is. Remember the requirement for an interference pattern.
Yeah.
An interference pattern requires a wave to pass through both slits simultaneously, spread out, and overlap with itself, canceling itself out in certain places so no light hits the dark stripes.
But I need to stop you because my brain is actively rejecting this. Every single photon was fired completely alone.
Alone in the room.
It was the only thing in the room. There was no second photon for it to bump into. There was no other way for it to cancel out with. It was a single, indivisible chunk of energy. How can one bullet go through two doors at the same time and crash into itself?
It should melt your brain. Honestly, if it doesn't, I am not explaining it right. The unavoidable, terrifying conclusion is exactly what you just said.
Seriously.
A single indivisible particle, a thing that by definition cannot be split in half, must have somehow approached the barrier, transformed into a wave of possibilities, passed through both slits simultaneously, interfered with itself in the empty space, and then, at the exact millisecond it touched the screen, snapped back into being a single solid bullet hole.
It is acting as a sprawling wave of potential while it travels, but as a solid physical object the moment it arrives.
That is the core mystery of quantum mechanics.
Okay, I refuse to accept this. I'm a logical human being. If I want to know how one particle can magically go through two slits at once, I'm just going to cheat.
How so?
I'm going to peek. I will buy a microscopic, highly sensitive camera. I will place it right next to the two slits, and I will just watch the photon as it goes through. I will catch it in the act of splitting in half.
That is the most natural scientific impulse imaginable. Like, let's just look at it.
Exactly.
But this leads us directly to the next monumental discovery, something physicists ominously call the measurement problem. Because the universe, it turns out, violently refuses to let you peek at the magic trick.
Okay. Walk me through exactly what happens when I turn my camera on.
You set up the exact same experiment, one photon at a time. But now you have a tiny detector sitting at the slits, designed to record a simple piece of data. Did the photon go through the left slit or the right slit? You fire the photon. The detector clicks. Left slit. The photon hits the screen as a single dot.
Okay, so it only went through one slit. It didn't go through both.
Correct. But here is the horrifying part. Because you measured which path it took, the photon stops acting like a wave entirely.
Wait, but?
You let the machine run for millions of photons. But this time, because your camera is on, the beautiful striped interference pattern at the back of the room completely vanishes.
It stops happening.
It vanishes. The screen behind the barrier now just shows two boring, massive clumps of dots. One clump directly behind the left slit, one clump directly behind the right slit, the exact pattern you would get if you were shooting a machine gun through two holes in a wall. Pure, classical, everyday physics.
Wait a minute, are you telling me that the simple act of me recording which path it took physically altered how the particle behaved in the air?
Yes, but it gets even stranger. What if you leave your camera sitting there, you leave it completely powered on, but you just unplug the hard drive so the data isn't recorded? You destroy the information about the path.
So the camera is running but not saving. What happens?
The wave-like interference pattern instantly returns.
The particle somehow knows if the information is being kept.
It definitely appears that way. The mere act of determining the path, extracting the information, destroys the wave behavior. And before you try to rationalize this by saying, well, photons of light don't have mass, they're basically ghosts anyway, maybe light is just weird, I need to clarify something crucial.
Oh boy.
This is not just a quirk of light.
Right, because physicists are obsessive, so I'm sure they tested everything else.
They have performed this exact double-slit experiment with electrons. Electrons are tangible bits of matter. They have mass. They have an electrical charge. They behave the exact same way.
They interfere with themselves?
They interfere with themselves until you look at them. Scientists have done it with entire intact atoms. In 1999, they did it with buckyballs.
Wait, what's a buckyball?
It's a massive, soccer ball-shaped molecule made of 60 carbon atoms.
A buckyball is huge on a microscopic scale. That's a massive physical object.
And it still acts like a wave of probabilities that goes through two doors at once, right up until the moment a detector measures it. This is not a light thing. This is a fundamental structural feature of reality itself. Whether it's energy or solid matter, at the microscopic level, the universe exists as a spread-out blur of possibilities when unobserved, and a strict, localized object only when forced to interact.
Okay, we need to decode the jargon that physicists use to try and make sense of this madness, because they have mathematical terms for this. When that photon or electron is flying toward the slits and we aren't looking at it, quantum mechanics says it is described by a wave function. What exactly is a wave function?
It's vital to understand that a wave function is not a physical wave. It's not a wave of water or a sound wave moving through air. You cannot touch it. A wave function is purely a mathematical object. It is a sprawling map of probabilities.
A map of probabilities.
Imagine it as a cloud. Before you measure the particle, the math says the particle doesn't have a single location. The wave function is a cloud that maps out every single place the particle could be and the exact percentage chance of finding it in any of those spots.
Okay, I follow.
When the photon goes toward the barrier, its probability cloud, its wave function, washes over both slits. The math goes through both doors. And it is those mathematical probabilities that are interacting and interfering with each other in the dark.
And the term for existing in this state of multiple possibilities at once is superposition. And I really want to nail this concept down because it is the most misunderstood word in science. I want to push back on a very common analogy.
Let's hear it.
A lot of people think superposition is like a magic trick, like a street hustler playing the shell game. There's a pea, and he hides it under one of 3 cups and shuffles them around.
I know exactly where you were going with this.
People think superposition just means the pea is definitely under one specific cup. We just don't know which one yet. They think the particle is secretly in one specific place, and the probability cloud is just a map of our own human ignorance. Is that what superposition is?
No. And distinguishing between those two ideas is the most important leap you can make in understanding quantum mechanics. It is emphatically not the pea under the cup. The reality is profoundly more unsettling. Superposition means that the particle genuinely, physically, objectively does not possess a definite location before you measure it.
The universe literally hasn't decided where it is yet.
Exactly. I'll give you a modern analogy. Think about playing a massive open-world video game. The computer disk contains the data for an entire planet, mountains, oceans, cities. But your computer's graphics card does not render the entire planet at once.
Right, that would crash the system.
Exactly. It only renders the sharp, high-resolution textures of the specific room your character is currently looking at. The rest of the world exists only as lines of code, as mathematical potential.
Wow, so the unmeasured particle is the unrendered video game map.
Yes. The particle is in a state of suspended potential. It is physically spread across all possible states at once. The physical universe does not bother rendering the final sharp location of the particle until something forces it to. And when that measurement occurs, when the photon smashes into the photographic screen, that entire sprawling mathematical map of probabilities instantly vanishes, and the universe renders one definite pixel.
That moment of rendering is what physicists call the wave function collapsing. The probability cloud instantly deflates into a single point of reality.
And the probabilities encoded in that math perfectly predict where the dots are most likely to land over thousands of tries, which is why the bright bands of the interference pattern build up in specific places. The math works flawlessly, even if the philosophical implications are terrifying.
Okay, I have a massive bone to pick here. I want to latch on to a specific vocabulary word we've used about 50 times in the last 10 minutes. Measurement. We keep saying the act of looking, or when a measurement happens, or when we peek with a camera.
You've spotted the trap.
Because if a particle only snaps into a solid rendered reality when it is measured, doesn't that imply that reality requires a conscious human being to be looking at it? Doesn't that put human consciousness at the dead center of physics? Because if reality only exists when a brain looks at it, we are basically living in a spiritual simulation.
We have officially arrived at the epicenter of quantum nonsense. You are opening the door to the biggest, most wildly pervasive myth in modern science, and we are going to slam that door shut right now.
Good. Because this specific idea that human observation changes reality has been massively hijacked by the wellness industry. This is the entire foundation of quantum healing or self-help books like The Secret or gurus on social media who tell you that your mind shapes physical reality.
It's everywhere.
They literally say quantum physics proves that looking at things changes them at a subatomic level, so you can manifest a sports car or cure a disease by collapsing the wave function of the universe with your positive thoughts.
It is exhausting. It is absolute, unadulterated pseudoscience. And the tragic part is, the confusion is entirely the fault of brilliant physicists from the 1920s who chose terrible vocabulary words.
Explain how the physicists messed up the words.
In the English language, the words observation and measurement strongly imply a human being with a clipboard. They imply a conscious mind, an eyeball, an intent. But in the strict mathematics of quantum mechanics, observation has absolutely nothing to do with consciousness. A human brain is utterly irrelevant to the equation.
So what does a physicist actually mean when they say a particle was observed?
In quantum mechanics, an observation simply means a physical interaction. Specifically, any physical interaction with the surrounding environment that causes information about the quantum system to leak away. It is just an exchange of energy or data between the particle and the rest of the messy universe. That's it.
Okay, ground this in physical reality for me. If a conscious human isn't the observer, what else can be an observer?
A literal rock can be an observer. A mechanical piece of plastic in a camera can be an observer.
What about a single stray molecule of oxygen in the air?
Yes. If our delicate photon in superposition accidentally bumps into a random oxygen molecule floating in the room, that physical bump transfers energy. Information about the photon's location is transferred to the oxygen molecule. Boom! An observation just occurred. The wave function collapses.
Wow.
The universe was measuring itself perfectly fine,
Yeah.
collapsing wave functions and generating solid reality for billions of years before monkeys evolved brains complex enough to think about it.
So it is not about the magic of the human soul. It is about physical entanglement with a messy, chaotic environment. And there is a technical term for this process of the environment ruining the quantum magic. Let's define it. It's called decoherence.
Decoherence is the great destroyer of quantum weirdness. To understand it, let's think about why that photon could interfere with itself in the first place. When it acts as a wave of probabilities, those probabilities have a perfectly precise mathematical rhythm to each other. Physicists call these phase relationships.
What is a phase relationship?
Imagine a perfectly choreographed, synchronized swimming routine in a calm, pristine indoor pool. 50 swimmers moving in absolute mathematical unison. That delicate synchronization allows them to create beautiful, complex patterns on the water. That is our isolated quantum particle.
But a science lab, or the real world, is not a pristine indoor pool.
Not at all. The real world is a boiling, chaotic ocean during a hurricane. Heat, stray magnetic fields, air molecules, cosmic rays. The moment our delicate synchronized swimming routine, the quantum system, is forced to interact with that chaotic ocean, the environment, what happens?
A giant wave crashes into the pool and the swimmers scatter. The synchronization is destroyed.
Exactly. The precise phase relationships are scrambled. The quantum information leaks out into the vast, messy environment and is lost forever. That scrambling process is decoherence.
I see.
The moment decoherence happens, the superposition breaks down, the wave-like behavior vanishes, and the system instantly starts behaving like a normal, boring, solid, classical object.
So to summarize this for everyone listening, your mind is incredibly powerful in many ways, but it is not collapsing wave functions through the power of thought. A grain of dust is collapsing wave functions simply by bumping into things. Anyone using the word quantum to sell you manifestation techniques is trading on a century-old mistranslation.
I couldn't have said it better myself.
Okay, but this concept of decoherence raises a genuinely fascinating logistical question. If bumping into the environment is what ruins the quantum fuzziness and forces a particle to pick a definite state, does that imply that the fuzziness is just a technological problem?
Where are you going with this?
Well, if we could somehow build a perfectly isolated vacuum and we developed infinitely delicate tools so gentle they could measure a particle without bumping it, without causing decoherence, could we finally see the whole picture? Could we measure a particle's exact location and its exact speed at the exact same time, restoring our perfect clockwork universe?
That is a highly logical, deeply intuitive question. And it transitions us perfectly to the next pillar of quantum mechanics, a concept that is almost as famous and almost as misunderstood as the double-slit experiment itself. I am talking about Heisenberg's uncertainty principle.
The famous uncertainty principle.
And the devastatingly short answer to your highly logical question is no. Even with magic, perfect, infinitely gentle tools, you cannot know everything.
Okay, let's lay out the basic definition of Heisenberg's uncertainty principle before we tear it apart. Formulated by Werner Heisenberg in 1927, it states that there is a fundamental limit to how precisely you can simultaneously know certain pairs of physical properties of a particle. The most famous pair is position, exactly where the particle is, and momentum, exactly where it is going and how fast it is moving.
And the rule is a seesaw. The more precisely you pin down where a particle is, the less precisely you can possibly know its momentum, and vice versa. If you know exactly how fast it's going, you are utterly blind to where it currently is.
Now, you said my question about gentle tools was intuitive, because the explanation I was just using is exactly how this is taught in most high school science classes. It's often called the clumsy scientist effect.
Yes, the observational disturbance theory.
Right. The analogy I always hear is trying to find a tennis ball in a pitch-black room by swinging a baseball bat around. You can't see the ball, so you just swing the bat. Eventually, whack, you hit it. In that exact millisecond, you know the ball's position. But the sheer force of your baseball bat has knocked the ball across the room, completely ruining its previous momentum.
It makes sense on a macro scale.
Right. So the uncertainty is framed as a failure of our bulky human tools. We just hit things too hard when we look at them.
And I want to be fair to high school science teachers. That clumsy measurement effect is a real physical phenomenon. Bouncing a photon of light off an electron to see it does literally impart physical momentum to the electron and bump it away.
Yeah.
But, and this is a monumental but, that clumsiness is not what the uncertainty principle is actually about.
So Heisenberg wasn't just complaining about bad microscopes.
Not at all. The profound truth of Heisenberg's principle is infinitely weirder than human clumsiness. The truth is that the particle literally does not possess a precise position and a precise momentum at the same time.
It just doesn't have them.
Right. It's not that those numbers are hidden from us or that our bat is too big. It is that the universe itself has not assigned both of those numbers to the object simultaneously. There's nothing definite there to be found.
Okay, that sounds like abstract philosophy. The universe doesn't know. I need you to explain how a physical object with mass can just not have a speed and a location.
We can explain this entirely through the mechanics of waves, because remember, everything at this scale is a wave function. So let's step away from quantum mechanics for a second and just look at a normal, everyday wave. An audio wave, a sound recording.
Okay, an audio wave, I'm with you.
Think of a perfect, sustained musical note. Let's say a singer hits a perfect middle C and holds it for 10 seconds. That musical pitch, the middle C, is the wave's frequency. In our quantum analogy, frequency and wavelength are the exact same thing as momentum. So a perfect pitch is a perfect momentum.
Got it. Pitch equals momentum.
But ask yourself this. When exactly did that middle C happen? At what specific microsecond?
I can't answer that. It didn't happen in a microsecond. It was spread out over 10 entire seconds.
Exactly. To have a perfect pure pitch, The sound wave must repeat its pattern over and over again. It requires duration. It must be spread out over a large amount of time. You cannot have a pitch that only exists for 1/1000th of a second because a wave can't oscillate in that short a time.
That makes total sense.
So absolute precision in pitch momentum requires extreme fuzziness in time and position. It's spread out everywhere.
So what if I want the opposite? What if I want a sound that happens at one exact, precise, mathematically sharp millisecond in time? A perfect position.
To get a sound that occupies an incredibly precise, localized point in time, you have to create a sharp transient, like a gunshot or a sharp clap of your hands.
Okay, a hand clap has a very precise time position.
But if you take a hand clap and run it through audio analysis software, what is its musical pitch? What note is a clap?
It's not a note. A clap doesn't have a pitch. It's just a burst of white noise.
Yes. Mathematically, to create a sharp, isolated spike, a precise position, you have to mix hundreds of different frequencies and wavelengths together so they cancel each other out everywhere except in that one tiny fraction of a second.
Oh, wow.
By combining all those different pitches to pinpoint the position, you have completely destroyed any single definable pitch. The momentum becomes a jumbled, chaotic mess of white noise.
That audio analogy absolutely unlocks it for me. It's not a failure of our tools. It is an unchangeable mathematical limitation of what a wave actually is. You can be a clear, sustained musical note, which means you have a perfect momentum, but you are spread out everywhere. Or you can be a sharp, chaotic hand clap, which means you have a precise location and time, but your momentum is just jumbled noise.
You've nailed it.
You mathematically cannot be a perfectly sustained note that only exists for 0 seconds.
The universe simply does not allow a wave function to be infinitely small and perfectly rhythmic at the same time. It is a hard mathematical limit on the resolution of reality itself. When you demand to know the exact position of an electron, you are forcing it to become a hand clap. The universe responds by scrambling its momentum into white noise.
It's breathtaking how the universe protects its own fuzziness. All right, so we've covered incredible ground. We've talked about how isolated particles behave like waves going through two slits. We've talked about how they interact with their environment and decohere into solid reality. And we've talked about the fundamental blurriness of their properties. But all of this has been about single particles acting alone.
And things get drastically stranger when they stop acting alone.
What happens when two quantum particles interact directly with each other and become fundamentally linked?
You are opening the door to what is arguably the most famous and the most fiercely debated phenomenon in all of quantum physics: entanglement.
Okay.
Albert Einstein famously despised this concept so much, he mockingly called it spookhafte Fernwirkung, which translates to spooky action at a distance.
Spooky action. I love that Einstein resorted to calling things spooky. Let's define entanglement. What actually happens?
Entanglement occurs when two particles, say two electrons or two photons, are created together or interact in such a way that their quantum states become mathematically inseparable. They become deeply correlated.
Inseparable how?
Once they are entangled, you can no longer describe them as two independent probability clouds. They merge into one single unified quantum system, regardless of how much physical space you put between them.
Okay, let's push this to the extreme to see why it drove Einstein crazy. Let's say I entangled two photons here in a laboratory on Earth. I trap one photon in a highly reflective box and leave it on a desk in New York. I trap the other photon in a similar box, put it on a rocket, and shoot it all the way to a laboratory on Mars. They are still entangled.
They're still mathematically one system.
So, millions of miles apart. If I open the box in New York and I measure my photon, let's say I measure a property called spin, and my photon is forced to collapse its wave function and become spin up. What happens on Mars?
Instantly, in the exact same microscopic fraction of a millisecond that your Earth photon becomes spin up, the photon on Mars will collapse out of its fuzzy superposition and definitively become spin down.
Instantly.
Instantly. They will always perfectly correlate. Measuring one instantly forces the other to adopt a corresponding state, no matter how much vast empty space separates them.
Okay, I am fully on Einstein's side here. I completely understand why he hated this. Because Einstein's masterpiece, the theory of relativity, is built on one inviolable law. The absolute speed limit of the universe is the speed of light. Nothing, no physical object, no signal, no information can travel faster than light. It takes light minutes to travel from Earth to Mars.
And yet, entanglement seems to imply that the Earth particle is somehow instantly teleporting a faster-than-light message to the Mars particle saying, hey, I just got measured as spin up, so you need to instantly drop what you're doing and become spin down.
It shatters the speed limit of the cosmos.
Einstein found this entirely unacceptable. He believed so deeply in the speed limit of light that he argued quantum mechanics must simply be an incomplete theory. He proposed a very logical alternative explanation called hidden variables.
Let's create an everyday analogy for Einstein's hidden variables to see how much common sense it makes. It's not about spooky teleporting messages. Let's imagine I have a pair of winter gloves, a left glove and a right glove.
A classic perfect analogy for hidden variables.
I take these two gloves, and without looking at them, I put them into two identical sealed envelopes. I shuffle the envelopes, I keep one envelope here in New York, and I mail the other envelope to my friend on Mars.
So they are separated by millions of miles, and they are in a state of unknown potential to the observers.
Exactly. A year later, I open my envelope in New York. I look inside and see the left glove. Instantly, at that exact millisecond, I know with absolute 100% certainty that the envelope on Mars contains the right glove.
You do?
Now, did my act of opening the envelope on Earth magically transmit a faster-than-light, spooky signal to Mars, physically transforming a formless blob of cotton into a right glove?
Of course not.
No. The gloves had pre-agreed on their states the moment I put them in the envelopes. They were always a left glove and a right glove the entire time they were flying through space. They carried hidden variables with them. We just didn't know what that information was until we looked.
That is a flawless summary of Einstein's argument. He firmly believed quantum particles were exactly like those gloves. When the two photons interacted on Earth, they essentially traded a secret pre-written script.
They knew what they were going to be.
Right. They carried these hidden, predetermined properties with them. The spooky action was just a comforting illusion born of human ignorance. It is a highly logical explanation that perfectly preserves the speed of light.
It is brilliant. It makes total sense, but I have a sinking feeling it's wrong.
It's entirely demonstrably wrong. And the story of how the scientific community proved Einstein wrong is one of the greatest experimental triumphs of the 20th century. It all hinged on an Irish physicist in the 1960s named John Bell.
Bell's theorem, this is legendary stuff. How did he prove Einstein wrong? Because you can't just peek inside the envelope while it's flying to Mars, right?
Exactly. You can't measure them without collapsing them. But Bell devised a brilliant, almost diabolical mathematical test. He figured out a way to statistically prove whether the particles were carrying pre-written scripts like the gloves, or if they were genuinely remaining in a fuzzy, undefined superposition until the exact moment of measurement.
I need an analogy for how Bell's math actually tested this without peeking.
Think of it like a cosmic casino game. Imagine two magical scratch-off lottery tickets. These tickets don't just have one thing to scratch. They each have three different hidden boxes. Box A, Box B, and Box C.
Okay.
You give one ticket to Alice on Earth and one to Bob on Mars.
Okay, two separated scratch-offs.
Now, if Alice and Bob randomly choose to scratch the exact same box on their respective tickets, say they both scratch Box A, they always, 100% of the time, reveal the exact same symbol, a cherry and a cherry.
Which Einstein would say proves they were printed identically at the factory. Hidden variables.
Right. But Bell said, let's change the game. Let's have Alice and Bob randomly scratch different boxes. Alice scratches Box A. Bob scratches Box AC. Bell used standard, indisputable statistics to prove that if the tickets were printed with pre-written hidden scripts at the factory, they could mathematically only produce matching symbols a maximum of 67% of the time when playing this mixed box game. It is a hard statistical ceiling.
So if they're pre-printed gloves, they cannot win the mixed game more than 67% of the time.
But when physicists actually ran this experiment with entangled photons, effectively scratching different boxes by measuring them at different quantum angles, the particles didn't match 67% of the time. They matched closer to 75% of the time.
They broke the statistical speed limit?
They completely shattered it. And the only mathematical way to beat that 67% limit is if the tickets are not pre-printed. The only way to win 75% of the time is if the scratch-off ticket on Mars is actively, instantaneously changing its underlying code based on which box Alice chose to scratch on Earth.
That is unbelievable. So Einstein was wrong. There are no hidden variables. There is no pre-written script.
It took decades of incredibly precise experiments to run Bell's test flawlessly, closing every possible loophole. This work was so profound it culminated in the 2022 Nobel Prize in Physics. The conclusion is absolute. The particles are not like the gloves.
So what are they like?
When they are separated across space, neither particle has a definite state. They are formless blurs. But the moment you measure the one on Earth, it rolls the cosmic dice, randomly decides its state, and the particle on Mars instantaneously adopts the corresponding state. The correlation is real, active, and happens in real time across the void.
Okay, wait. I am slamming on the brakes. If they are genuinely actively correlating their states across millions of miles in real time, 0 seconds flat, doesn't that fundamentally break relativity? Doesn't that prove information is traveling faster than light? Did quantum mechanics just destroy Einstein's greatest theory?
This is the ultimate cosmic loophole, and we must explain it carefully to protect relativity. The answer is no. You are not breaking the speed of light, and you cannot use entanglement to send a faster-than-light text message to Mars.
Why on Earth not? If I poke the particle on Earth, Mars instantly reacts. If he reacts, why can't I use that to tap out Morse code? Ones and zeros, up and down.
Because you cannot control the outcome of your own measurement. Remember Heisenberg. Remember the fundamental randomness of the wave function collapse.
Oh, right.
When you measure the particle on Earth, you cannot force it to be spin up to send a 1, or force it to be spin down to send a 0. The result is inherently, fundamentally random. It is exactly like flipping a coin.
Okay, I think I see where this is going.
So you measure your Earth particle, and it randomly comes up tails. You know for a fact the particle on Mars just instantly became heads. But think about the experience of the scientist on Mars. What do they see?
They just see their own particle turn into heads.
Exactly. They measure their particle, and they get a random head. They have absolutely no idea if they got heads because you forced a collapse on Earth, or if their particle just naturally collapsed into heads completely on its own. It's just a random coin flip to them.
Ah, so the correlation is completely invisible in the moment.
Precisely. The only way you can prove that the spooky correlation actually happened is to call the scientist on Mars on a regular, slower-than-light radio telephone. You have to say, hey, I forced a measurement and got tails at exactly 3 p.m. And they look at their data and say, wow, I measured mine and got heads at the exact same millisecond.
You have to compare notes using slow communication.
The pattern only becomes visible after the fact, when you bring the two classical sets of data back together at the speed of light. Therefore, no actual, usable, controllable information traveled faster than light. The universe allows this instant magical connection, but strictly forbids you from ever using it to send a message.
That is just brilliant.
Relativity survives entirely intact. It is a breathtakingly elegant compromise by the cosmos.
My mind is completely blown. It is so elegant, but so infuriating. I want to pivot drastically here, because all of this, the double slits, the wave functions, the cosmic scratch-off tickets, the spooky action, it sounds incredibly exotic. It sounds like pure, abstract, theoretical philosophy cooked up by physicists in ivory towers who have too much time on their hands. Why should I, or the person listening to this while doing the dishes or walking their dog, actually care about any of this today?
That is the most important pivot we can make. We must ground this in the listener's immediate reality. Quantum mechanics is not an exotic curiosity. It is not abstract philosophy. It is the literal load-bearing infrastructure of the modern world. Without an exact, rigorous mathematical mastery of these bizarre quantum behaviors, the 21st century simply does not exist.
Let's run through the specific applications.
Yeah.
First and foremost, the absolute foundation of the digital age, the transistor.
Every computer, every smartphone, every massive server farm powering the internet, AI, and global finance is built from billions of microscopic transistors. A transistor is, at its core, just a tiny electrical switch that turns the flow of electricity on or off, creating the ones and zeros of digital logic.
But classical physics can build a switch. A light switch is classical physics.
A macroscopic light switch is classical. But when you shrink a switch down to the size of a few atoms, classical physics completely fails. To make a modern transistor work, engineers have to manipulate a deeply quantum phenomenon called quantum tunneling.
Oh, this sounds cool. What is quantum tunneling?
In classical physics, if you roll a tennis ball at a thick brick wall, it bounces off. It does not have the energy to go through. In a transistor, we have a barrier that electrons shouldn't be able to cross. But remember, the electron is not a solid tennis ball. It is a wave function, a probability cloud.
Right, it's a blur of potential locations.
When that probability cloud hits the microscopic barrier in a transistor, the math says a tiny portion of the cloud actually bleeds through to the other side of the wall. There's a non-zero probability that the electron is already on the other side.
Really?
And if you apply a precise voltage, the electron will literally vanish from one side of the solid barrier and instantly materialize on the other side without ever passing through the space in between. It tunnels through.
It walks through solid walls like a ghost.
Yes.
Yeah.
Your phone's processor relies on billions of electrons doing this ghostly quantum tunneling billions of times a second. If they didn't act like probability waves, the switch wouldn't work. Your phone is a quantum mechanics machine.
What about lasers? Lasers are everywhere, from the barcode scanner at the grocery store to the fiber optic cables that are currently transmitting this audio file across the world.
Lasers are pure applied quantum mechanics. Remember Max Planck's original discovery? That energy comes in exact, discrete staircase steps.
The vending machine coins.
Right. A laser works by pumping atoms with energy so that their electrons jump up to a higher quantum step.
But they can't stay there, right? They want to fall back down.
Exactly. When one electron falls back down to a lower step, it releases one exact, indivisible photon of light. But because of quantum rules, that one photon can trigger other elevated electrons to fall down at the exact same time, releasing identical photons.
Oh, wow.
It creates a quantum avalanche of perfectly synchronized light waves all marching in step. Without the discrete, quantized energy levels of the atom, you just get a messy glow like a light bulb. You do not get a laser.
Let's talk about medicine. If you or a loved one has ever had an MRI scan to look inside the human body without surgery, you owe your diagnosis to quantum mechanics.
MRI stands for magnetic resonance imaging, and the entire technology relies on a deeply quantum property of atomic nuclei called spin. It's not physical spinning like a top. It's a purely quantum property that makes atoms act like tiny microscopic magnets.
So how does the machine use that quantum property?
When you lie inside the giant tube of an MRI, its massive magnetic field forces all the tiny quantum spins of the hydrogen atoms in your body's water molecules to align in one direction. Then, the machine shoots a perfectly calculated radio wave at you. This radio wave is the exact quantum packet of energy needed to knock those spins sideways.
And when the radio wave turns off?
The spins snap back into alignment with the big magnet, and as they snap back, they undergo a form of quantum decoherence, releasing their own tiny photons of radio energy.
The machine listens for those.
Yes, it listens for those faint quantum echoes. Because bone, fat, and tumors have different amounts of water, they release different echoes. A computer compiles those quantum signals into a perfect 3D picture of your internal organs.
That is miraculous. And if we want to zoom out even further from human technology, look at nature itself. The very fact that atoms are stable, the structure of the periodic table, the exact angles of the chemical bonds that form your DNA, all of it is dictated by quantum rules, specifically things like the Pauli exclusion principle, which dictates how electrons stack up in those probability clouds.
Even the sky above you. Consider the sun. The sun produces energy through nuclear fusion smashing hydrogen protons together to make helium. But protons are positively charged. They violently repel each other, just like two north poles of a magnet.
Right, classical physics would say they repel each other before they can ever touch and fuse.
And classical physics calculates that the core of the sun is actually not hot enough or dense enough to force them together.
Yeah.
Classically, the sun should not shine.
So how does it?
Quantum tunneling. Just like the transistor. The protons act as fuzzy probability waves, and occasionally they go through each other's repulsive force fields and appear close enough to fuse. Without that quantum fuzziness, the sun goes dark, and life on Earth never exists.
The economic and existential impact is staggering. Estimates suggest that tens of % of the entire global economy, trillions upon trillions of dollars, rests directly right now on our understanding of quantum technology.
It's hard to even wrap your head around.
Okay, we've covered a monumental amount of ground today. I think we need to do a rapid conversational recap to lock all these puzzle pieces into place for the listener. Let's summarize the undeniable facts.
Good idea. Let's do the cheat sheet.
Okay, the quantum cheat sheet. Number 1. At the smallest scales, physical objects do not have definite properties until they are forced to interact with their environment. Number 2. When left unobserved, matter and energy behave as spread out, mathematical clouds of probability that can literally pass through 2 doors at once and interfere with themselves.
Spot on.
Number 3. Because they are governed by wave math, certain pairs of properties, like precise position and precise momentum, simply cannot be sharply defined at the same time. The universe will not allow it. That's Heisenberg. And number 4. Particles can become entangled, sharing instant, real-time correlations across massive distances that completely defy any classical clockwork picture of the universe.
And the most vital takeaway of this entire deep dive is that every single one of those bizarre, brain-melting claims has been tested relentlessly for a century. They have been tested to extraordinary precision, and they have passed every single time.
But here is where we reach the final boundary of our deep dive, the unresolved core. Because for everything we've explained today about how quantum mechanics works, we have to draw a final humbling distinction.
We do. Because what quantum mechanics fundamentally doesn't tell us, what no equation has definitively answered in the last 100 years, is what any of this actually means underneath it all. Physicists have argued fiercely over the interpretation of these facts.
Give me an example of an interpretation.
Well, you have the Copenhagen interpretation, which roughly says, stop asking what it means, the math works, don't worry about reality until you measure it. But then you have the many worlds interpretation, which argues that the wave function never actually collapses.
Really?
Instead, it argues that every time a quantum measurement happens, the entire universe literally splits into branching alternate realities to accommodate every possible outcome.
So in one universe, the photon went left, and in a newly birthed universe, it went right.
Exactly. Is the wave function a real, tangible, physical fabric? Or is it just a mathematical spreadsheet tracking human knowledge? The why is an entirely unresolved, fiercely debated philosophical question.
But the how is indisputable. The mathematical theory works. The smartphone in your pocket, the MRI at the hospital, the sunlight hitting your face, these are the absolute undeniable proofs that the universe operates on these bizarre rules.
The interpretation is philosophy, but the engineering is undeniable reality.
Which leaves us with a final provocative thought. Something for you, the listener, to mull over long after you take your headphones off.
I love this part.
If absolutely everything, the microchips in your phone, the air molecules bouncing around the room you're in, the very atoms that construct your brain, your heart, and the solid hand you looked at the beginning of this deep dive, if all of it is fundamentally built out of these probabilistic, fuzzy, wave-like, entangled quantum pieces.
At what exact threshold of size does all that quantum fuzziness stop?
Exactly. Where is the line? If a buckyball made of 60 atoms can go through 2 doors at once, can a virus, can a grain of sand, at what exact tipping point does a chaotic cloud of probabilities suddenly solidify into the heavy, predictable, clockwork reality you and I experience every single day? We open our eyes and the world is solid, the apple falls straight down, we are made entirely of quantum mechanics, so why don't we feel like it?
It is the ultimate question of where the quantum realm ends and our everyday reality begins. And it is a boundary we are still desperately trying to map.
Thank you so much for joining us on this incredibly deep dive into the very fabric of reality. It is a lot to wrap your mind around, and if you are confused, you are in exactly the right place. The next time you look at a beam of light or tap the screen of your phone or just look at your own hand, remember that the universe is far stranger, far less certain, and far more magical than it appears on the surface. Keep questioning the world around you. We'll see you next time.